Okay, so we're looking at a little side lesson here related to the least squares regression equation and how it came into being. Right? So we're going to use partial derivatives to develop the regression model. Right? So easier said than done, because in a stat class, there is really no expectation that students would have a background in calculus. So what I'm going to do is, or at least not much of a background in calculus, so I'm going to teach some aspects of partial differentiation, only the relevant ones, but there is the expectation or the hope that you would have some understanding of derivatives going into this. All right. So the best fit, linear fit in a least squares sense minimizes the sum of squared residuals, right? So that's kind of a overarching concept here, which doesn't really mean too much just yet. It will in a page or so, but at the moment, that bold word minimizes. Right? That should speak to the concepts associated with calculus. Right? Optimization, maximums, minimums. That's a pretty typical concept that's covered in calculus courses. All right. A residual is the difference between an observed value and the fitted value provided by the regression model. So we're talking y minus y hat. All right, so when I say the best fit in a in a least squares sense minimizes the sum of the squared residuals, I'm talking about the sum, as in a summation, of the residual values squared. All right, that's a very shorthand way of writing it, but that's the general gist of it. All right. The issue that comes about is that we're going to end up with multiple variables in the expression that we're going to use to develop the minimum relationship. Right? Whenever you're dealing with multiple variables, multivariable functions, you're most likely going to be using partial differentiations, partial derivatives, to analyze those. All right, so that's what we need to kind of talk about first. I didn't want to give you a function just kind of out of the blue without giving a little bit of background on it. So in that first example, it says find the indicated partial derivative for the function f of x, y, f of x comma y, which is a function that's not only in terms of x, but also in terms of y, that is equal to xy squared minus x. What it's indicating for us is that both x and y serve as a variable within this function. All right. This would also be known as z equals xy squared minus x. All right. So what I did was I popped that into Geogebra just to give you a sense of what that function would look like. All right. So it's a multivariable function in that it's dependent on multiple variables. Right? So it's a function of two variables rather than a function of a single variable. In order to find a partial derivative, so we use the lowercase delta notation instead of ordinary d, dy dx, df dx. We say delta f delta y, delta f delta x. What that's saying is hold one variable constant and differentiate in terms of the other. All right, so in this one, the interpretation is hold y constant, then differentiate with respect, if my pen works, to x. All right. And the value of doing that is it allows you to work along a particular path associated with whatever the y value is constant at. So let's say y is equal to 2. Then I'd be looking at the single variable function 4x minus x, or you just simplify down to 3x, just replacing the y with a 2. It could be even simpler, where y is equal to 0. right? In which case you get the single variable function, f of x equals negative x. Bottom line is, you're treating the y as constant, which allows you to focus just on what kind of change is happening in terms of x. And then if we wanted to evaluate later on, we could. All right, so what I'm going to do is I'm going to rewrite the function. I'll use my notation, df dx. So that's going to tell me to essentially treat the y as if it's just an ordinary constant multiplier. All right, so if this were x times 2 squared, you know what the derivative would be, because 2 squared would be 4. The derivative of 4 times, or x times 4 is, you're really looking for the derivative of 4x would just be 4. All right, if you treat the y squared as a constant, we could write this in a slightly different way. Y squared times x minus, I'll write the 1 here, minus a 1 times x. All right, the constant multiple rule tells us hang on to any constant multipliers. All right, so I'd have the y squared and the negative 1, and just multiply those constant multipliers, multiply the multipliers, by the derivative of the parent function. All right, derivative of x is 1 in both cases. Clean it up, and we have the partial derivative here of y squared minus 1. All right, so basically, only differentiate the x portion of each term. All right, there are exceptions to that because sometimes you get into product rule and quotient rule and all that stuff, but that's the general idea. All right, so for the second example, I'm going to hold x constant and differentiate with respect to y. That's what my notation is telling me to do. So I'm going to hold x constant. I'll make little modifications, special modifications. All right, so that means that the x values here are thought of as constant multipliers. And actually, in this case, this is just a constant period. So when I want to find the derivative of this function with respect to y, my deltas tend to go off the rails sometimes. They either end up looking like D's or they end up looking like 8's. All right, so I'm going to hang on to my constant multiple here, bring that down, all right, and we'll differentiate the y squared, which will now become a 2y. The derivative of any constant, standalone constants, go to 0, so that's that. And so my partial derivative with respect to y is 2xy. All right, so if we know what y is for part A, then we know what the rate of change is for the multivariable function for the surface per instantaneous change in the x direction. And the same holds true for B, but you're holding x constant. So if we knew what x was, we would know what the rate of change is in terms of y. Right? The only difference between the two, really, is that in the case of A, since your partial derivative is strictly in terms of y, if you know what y is, it's telling us that your partial would be constant. If you know what x is, in the case of part B, you sub that in, but you're still going to have a variable partial. All right, so that'll change depending on where you are in terms of y. All right. There's a lot more to that, but that's the general process. All right. And you can see something like in number 2, it looks a whole lot spicier, but if you follow the same general principle, oh, found a little typo for somebody. The worst part is, I knew I had to fix this when I was editing the document. I put it on my list of things to do, and then I just deleted my list of things to do. So we're still holding y constant. This is all true. Everything I wrote here is true. I'm going to rewrite the function so I have something to highlight. E to the x sine of y minus xy. I'll write it twice. Now for this one, the one on the left, I'm differentiating again with respect to x. All right, so any instance of y is treated as constant. All right, so we're treating this as a constant, and we're treating this as a constant. Whereas in part B, we're differentiating with respect to y, which means every instance of an x is treated as constant. All right, so I kind of think of it as differentiating around the y's and differentiating around the x's. All right, so if I look at this and I say, okay, ignore the y's for now. What's the derivative of my x stuff? Well, e to the x has a derivative that's e to the x. Bring down the sine of y. Negative x has a derivative of -1. Bring down just the y. Clean it up if you want, or maybe don't even write the 1 to begin with. E to the x sine of y minus y. All right, with partial derivatives, you might look at something and think implicit differentiation, but then upon further review, you realize it's not. All right, so partial derivative with respect to y, I'm going to hang on to my e to the x, differentiate around that. Derivative of sine of y is cosine of y. Bring down the e to the x. Differentiate around the x, so I'm going to leave the x alone, differentiate the y with respect to y goes to 1, so this becomes just a minus x, and that would be our partial derivative. And just if you're curious, this surface looks like this. I mean, it's pretty wonky, a lot of nooks and crannies. And so depending on what x value you're dealing with, depending on what y value you're holding constant, and vice versa, it'll give you a different path to journey along. So for example, I can give you a quick look at that. Let's say, for example, I'll give you like a hypothetical. Let's say, suppose poor quality suppose, until how often I write that word. Very textbooky. Suppose y is equal to 0. All right, so I can do that. Y equals 0. Now that's assuming my GeoGebra is not going to glitch on me, which happens more times than I would like. All right, that creates a plane, all right, in 3 dimensions. When you put in an equation that looks an awful lot like a vertical or horizontal line, in 2 dimensions, this would be a horizontal line. In 2 dimensions, y equals 0 would assume all values of x are true. So from -infinity to infinity. That's why it extends outward forever. The thing is, in 3 dimensions, there's 2 variables that are unaccounted for. So what we're saying here is that y is equal to 0, yes, but that's true for all values of x and all values of z, all right, because it goes up and down forever too. So this will go from negative infinity to infinity in terms of x. It'll also go from negative infinity to infinity in terms of z, which creates a plane, all right? So it creates a rectangular infinite surface, right? So where it intersects, and it's kind of hard to see, but where it intersects with the surface can create a trace, a cross section, if you will. Now here it looks like it's right on the axis, but that could be misleading. All right, but as you look at it from the different perspectives, you see basically where it goes from purple to greenish. You can see that there's definitely an instance where it slices right on through. All right, so if I evaluate this partial derivative for quality when y is equal to 0, now that vertical line just means, as you hopefully know, from any exploration involving integration or substitution involving calculus, that vertical line means such that or given that y is equal to 0, we're just substituting in here, you get a result of 0. All right, and that's the rate of change. So what that's telling us is along that path that's created by the intersection of the plane and the surface, that path can be decomposed into a curve in 2 dimensions. But really all you're thinking about is you have this purple giant wobbly piece of jello and you cut through it with a knife. All right, that outermost edge of, I don't know why I'm gesturing in the air, the outermost edge of that jello created by that cut, that slice, is a pathway, all right? It creates a curve. What this will do by making this substitution, it'll allow us to determine the rate of change just on that pathway, just on that curve. In this case, the curve happens to be the x-axis, all right? That red axis is the x-axis, the green one is the y-axis, and the blue one is the z-axis. That might be the missing bit of context, because Geogebra is weird in that it doesn't automatically label the axes unless you tell it to, all right? So what you can do, if you're interested in this topic, is you can play around with a variety of different numbers as a value to slice into your surface and just get a feel for what the intersecting curve would look like. For example, if it's not going to let me, but if I change my y to equal 2, that's going to shift it a little bit from our perspective here, a little bit to the right. What is that going to look like in terms of an intersecting curve? You know, that's part of the fun.